To know the theory behind the Brewster's angle experiment, first we should know what do you mean by polarization. Polarization is nothing but the phenomenon in which vibrations of light waves are restricted in a particular plane. Okay, so we know that light is made up of light has both particle nature and wave nature. So let us consider a particle nature that the particle will have different orientations of vibration that is known as an unpolarized wave. And when you orient that vibration in a particular direction, one particular direction, it becomes a polarized event. In the same way, let us see in the form of wave. Here we have a wave which is in both longitudinal and transverse orientation. That is unpolarized because it is having two orientations. When you polarize it, it will have only orientation in a one particular direction. So this is what we mean by polarization of light. Now let us come to Brewster's law. What does it tell us? This law describes the angle at which unpolarized light upon reflecting from a surface becomes completely polarized. Means when we are reflecting, when the light is incidentting on a surface and getting reflected, that reflected ray is getting polarized. This is what we mean by the Brewster's law. And it happens at a particular angle. That particular angle is called as Brewster's angle. So let us learn more about Brewster's angle. If we incident an unpolarized ray on the reflecting surface, a part of light will get reflected and a part of light will get refracted. And an unpolarized will have different kind of orientations as we know. So let us consider it as a perpendicular and parallel orientation. If here perpendicular orientation is represented by a dot, parallel orientation is represented by an arrow. So an unpolarized light is having both perpendicular and parallel orientations. And when you incident this light at a particular angle, which is called as Brewster angle, the refracted ray will be partially polarized because it will have parallel components and a little bit of perpendicular components. Whereas at Brewster's angle, the reflected ray will completely have perpendicular component of the light. So when you incident a light at the Brewster's angle, the reflected ray will give you a polarized light. And when we come to the conditions of the Brewster's angle, the reflected and refracted rays are at 90 degrees to each other, which is nothing but perpendicular to each other. And the component of light with electric field parallel to the plane is incidence is not reflected at the center, and only the perpendicular component is reflected, and the parallel components are being refracted. Thus, the reflected light is linearly polarized, and reflected light is partially polarized. Now, let us see how do we arrive at the expression for Brewster's angle, which is nothing but theta b. So, here we are having two mediums. So we can use Snell's law here, right? So what is Snell's law tells us? N1 sin theta 1 is equals to N2 sin theta 2. N1 and N2 are nothing but reflected in excess of first medium and second medium. Theta 1 is angle of incidence and theta 2 is angle of refraction. So using Snell's law, we can derive this Brewster's angle. And we know at Brewster's angle, reflected and refracted rays are at 90 degree. Yes, reflected and refracted rays are at 90 degree. So, theta b plus theta d will be is equals to 90 degree because completely it is 180. So, if you remove this 90, then the remaining should also be 90. Then theta b plus theta d, which is nothing but angle of reflected ray and angle of refracted ray, will also be equals to 90 degrees. From then, we can arrive that theta t is equals to 90 degrees minus theta b. If we substitute this theta t value, angle of refraction in Snell's law, we get N1 sin theta b is equals to N2 sin 90 minus theta b. Yes, then N1 sin theta b is equals to sin 90 minus theta b is nothing but cos theta b. So N1 sin theta b is equals to N2 cos theta b. If we take common of it, send this to here, then it will be tan theta b is equals to N2 by N1. Using this formula, we can find the refractive indexes of a given medium if the Brewster angle of that particular surface is given to us. Okay. And the next formula, if you send the time to right hand, we'll get theta v, which is Brewster's angle, is equals to tan inverse into by angle, refractive index of second medium by first medium. Using this, we can find the Brewster's angle if we know the refractive indexes of the both medium.
This is setup for performing the Brewster's law experiment. Let's turn on the setup. And you can see that this is the laser light source. And the laser light is falling on the glass polarizer. And its reflection, and we can adjust it however we want. And the laser light is reflected and falling on the center of the photodetector. And the output is shown in the digital display there. And you can measure the angle using the goniometer. And we can adjust it however we want. So that was the overview of the setup. Now let us see how the experiment is performed. So first of all, let us adjust the angle and set it to 5 degree. And the whole setup should be stable throughout the experiment. And the reflected laser beam should fall on the center of the photodetector. When it falls on the center of the photodetector, we can observe the corresponding change in the output there. And we should note that down. For 5 degree, this is the output that we have got. Now we have received the measurement for 5 degree. Now let's make a 5 degree increment, that is 10 degree. And the corresponding output should be measured in the digital display. Continuing this way, with an increment of 5 degree, we should measure the corresponding output until we reach the angle of 50 degree. After reaching the angle of 50 degree, we should make an increment of 1 degree, that is 51, 52, 53 and so on, because the Brewster's angle falls within the range of 50 to 60 degree. So preferably 55, 55, 54 degree and so on. So we should make a 1 degree increment and the corresponding output that is shown in the digital display should be noted down. Also, we should make sure that the reflected laser beam should fall in the center of the photodetector in all these cases. And we should note down the output that is shown in the digital display for each of these angles.
So moving on to the observation and calculation, we have the calendar column here with the incident angle and the corresponding power, which is written in milliwatts here. And the calculation at Brewster's angle we have already talked about it. Tan theta is equal to mu by mu naught. Mu is nothing but the refractive index here. So we will get the equation mu is equal to tan theta naught. Theta naught is nothing but the minimum angle that we have got from the experiment. And about the body graph here, we have power in milliwatt in the y-axis and the incident angle in the x-axis. We get a graph like this, where the minimum output of the experiment will be the Brewster's angle. So here we have some experimental values. For 5 degree angle, we have 0.90, and similarly, we'll take all the other angles, and until and unless we get the minimum power, angle corresponding to the minimum power, we have to do it like that, and from there, we have to take intervals of 1 so that we can get to know what is the minimum deflection happening. Moving on to the calculation, we have at Brewster's angle, tan theta is equal to mu by mu naught. Mu is the refractive index of the material that we are using, and mu naught is the air medium, which is equal to 1. So mu is equal to tan theta naught, that is the minimum angle that we have got. And here it is 55, 0.33 is the minimum power that we have got. So the corresponding angle is 55. So mu is equal to tan 55, which is mu is equal to 1.4281. And talking about the graph, we have power in the y-axis and angle of incidence in the x-axis. And plotting the graph, we get the Brewster's angle as 55. And last but not the least, talking about the result, we have 2 points. The Brewster's angle is found to be 55, which is the minimum power that we have, power's angle that we have got, and the refractive index of the material, which is mu, that is 1.4281.